So today again I'll start your control unit design. Last class what I have done, uh, I have considered the very simple instructions, or you can say that very basic concept of your control unit design. Okay, there is nothing actually. That is a very simple. If you consider the instruction and how you can implement a little bit, I have explained. But today I want to consider the design for your, you can say that processor. But it is very difficult to consider the whole processing unit and what is the exactly consider the operations to execute an instruction. Okay, it is very difficult to consider, but for our convenience and so that we can understand the design of control unit, I will consider few basic operations and not the operations, I want to say that basic instructions, and for each instruction there may be required the the 10 or 15 control signals, but I would like to consider maybe the 5 and 6. Okay, now I want to start. So here you already you have seen this type of diagram, and repeated time I use this diagram because this diagram is common. And you have seen that central processing unit, we have the two part. One is the control unit, another is the arithmetic logic unit, and some supportive components. Not only the arithmetic logic unit can do all the operation, it can do the basic operation, that means addition, subtraction, multiplication and division based on the type of the processor, but it needs many supportive registers also. So same as any other system, whatever the system always has some inputs and some outputs. So for continuity design also, it can generate the control signal. It is very true. At the same time, it needs some inputs from different components of the different components, or you can say the different elements from the CPU as well as from the outside of the CPU. So control unit needs some control signals to control to generate the other control signals. So it needs some inputs, at the same time it generates some control signal to control the different elements inside the processor and outside the processor. Okay, so now, so you know that for a processor, mainly you have the three type of operations. So what is the phase, and as there is that interpretation of that instruction, what is the meaning, what is the exactly the meaning of the instruction, and next step is that execution. But for control design, we for control design or for control unit, that needs the to generate the different control signal for sequencing of the operations, and at the same time what is the operation, meaning of that, what to do, that is done by the control unit. Now uh, this is also known to you. What is the meaning of the instruction? Instruction is nothing but it is a opcode and operands, and it needs sometimes some addresses. So depends on the type of the machine, you can have the different type of the formats of your instruction, but normally we have the opcode and operands. Okay, now program counter, it is a very important register who control the basically sequence of execution of instructions, and sometimes it may be incremented by 1 and sometimes it may be incremented by k. You know that different type of the jump instructions are there, so it can jump to different addresses. So program counter will control will be in that way. Now next is that different way you can design the control unit. So mainly we can divide the two approach. One is the hardware approach, another is the microprogrammed approach. Hardware approach you can understand from the meaning, that is we can design a circuit. Okay, that circuit physically exists and you can design. It has some advantage. For example, it is a very high speed, but if you want to change something on that moment, it is very difficult. If you want to change the sequence of control signals, you cannot do. So for that, you can use another type of the control unit design, that is called the microprogram control unit. You know that for any instruction, it is executed with the help of set of operations. This set of operations, you can say that micro instruction, or you can say that micro operations. And that micro operations you can write in your special type of the memory, that is called the control memory. And it is a software approach. So if it is the software approach, you can understand easily. You can alter, if you want to alter the sequence of the control signals, on that moment you have to change the content of your control memory. And obviously it is a slower than the hardware, because it is a software approach. So wherever you use some software approach, on that moment the fetch and execution, so that type of operation always it will be involved. So obviously it will take some time. Now today I will explain the hardware control unit, how to design. Now first one is that state table method. For the state table method, I can give one example. Last semester in your digital electronics class, you have designed many circuits with the help of this, with the help of the state table. And obviously you have seen that that design is very much complex, and whatever the circuit, that is very big. So for that reason, we never use the state table. It is very difficult to manage all the inputs and outputs, and based on that you design the sequences circuit. Okay, so it takes the time, and at the same time very you can say that it is not so good manageable. So for that reason we never use this type of the circuit, but it is possible. You already have seen in your last semester class that with the help of D flip flop, T flip flop, you have designed many state table, and from that state table you have designed the circuit. Now next method is the delay element method. Delay element method, to describe this delay element method, first you try to understand that how to execute the instructions, whatever the instructions, and that may be add, arithmetic operation, the logical operation, that may be I have considered the AND operation, and different type of the load and store operation, that was data movement operation, different type of the branch instruction, that is jump, like that. So for all the instruction, you try to remember phase cycle is the same. Okay, so for each instruction, what is happened, that opcode basically stored in memory. So processor have to read that opcode from memory, and have to store into the instruction register. This process is known as the fetch operation. Okay, and what is the time required, that is called the phase cycle. Now for these instructions, what I have considered, but remember, for all the instructions you can do the same set of operations for your phase cycle. First one is that 0 is, that is the activate your CPU, and first is that program counter content goes to the address register, and from that address, data, that means opcode, will be stored into the data register, and that register obviously it will be stored in the instruction register. At the same time, program counter can be incremented by 1, or depends on the instruction, it will be incremented by k. So what is happened, these are the operations for your fetch. Fetch meaning is that read the memory for opcode. So opcode always stored in the instruction register, you have to remember. And here through this data register, it will store into the instruction register, and whenever processor will execute any instruction, automatically program counter will be incremented by 1, or that means the incremented to the address of the next instruction. You know that control unit is responsible for maintaining the sequence of instructions, how your program will be executed. Now here these 1, 2, 3, A and 3B, these operations are required for your fetch operations. Now suppose that load instruction. Okay, now if you have the load instruction, Here you can see that already you know load instruction meaning is that data will move from memory to processor. So where it will be loaded, okay, from where it will be loaded into the accumulator, isn't it? Load or stored, normally we use the internal register of the processor, that is the accumulator. So load means that loading into the accumulator from a address of your memory, and stored means that your content of accumulator will be stored for future use into a memory address. So for your load instruction, what has happened, first the address will be stored into the address register, then from that address the address data will be stored into the data register, and from data register to the accumulator. So these are the sub operations of your load instruction. Okay, so instruction is load, but with this will be executed with the help of the set of operations, okay, sub operations. So this is the load operations, 1 2 3, then 4 5 6 7 8. 8 means that go to the next address, that means again it will go to the fetch operation. Okay, now for the stored, what is happen, again it will stored meaning is the content of accumulator will be stored into your memory. So here is also required the address where it will be stored. So for that reason, goes first address go to the address register, and content of accumulator go to the data register. Ultimately it will do the operation content of accumulator through data register, it will be stored into the memory. So these are the sub operations for your store instruction. Now same as for your add, you can say add means that always we considered one of the operand is the accumulator, and another you can imagine that is inside a location of memory. So for that reason again memory read operation is required. So address will be stored into the address register, content of that memory location will be stored into the data register, then it will be added with the accumulator. So AC plus DR, content of accumulator plus content of the data register will be added, and it will be stored into the accumulator. Okay, now for the AND operation, same as your add operation, what is happen, again one of the operand is the accumulator, but for other operand it needs to access the memory. So for that reason again it will store the address register address of the operand, and from that address the data will come to the data register. After that processor can do the operation, that is a logical AND, AC logical AND DR. Okay, and that will be stored into the accumulator. So after completion of this instruction, it will again go to the fetch cycle for the next instruction. Now if the instruction is the jump is this is a unconditional jump. That means whatever the address, to that address program counter will be stored, and based with the help of the program counter program can be jumped to that particular address. Now data register should be stored into the program counter for that reason. Now another instruction, that is a jump Z. Z means that depends on the Z flag, the processor can jump to a particular address. So this is jump and jump Z implementation is the same, but before jump it will check the Z flag. So based on the Z flag, it will jump to a particular address. Now this is a complement. Complement, you know that complement most of the time use the operand, that is the accumulator. So content of accumulator will be complement, and that will be stored into the accumulator. So these are the instructions we can consider, and these instructions has the many steps, or it has a finite number of steps in a particular design of your system you can use. Okay, now if you have these structures, so on that moment we can write different control signals. Okay, just want to see this is a, we can say that this is a C0, this is a C1, this is a C2, this is a C3. Just give the name of the control signals. Now here the C4, C1, C5, Here is also C4 because this is the same type of operation, and this is the C1 because this is the same. This C1, these two operations are same. Operations are same means that the same unit is doing the same this operation. Okay, same component you can utilize for this operation. Now next is that C6 and this is C7. Again, it is a C4. See that all the C4 are the same operations. Okay, and it is a C1. C1 is also that is a memory content of memory, but that is memory read operation. You can say it is a ultimate execution operation. And here is also you have the C4, you have the C1, and this is the different. That's why after C8 you have the C9, and it is a different from others. That's it is a C10, and here is also you can say that only the based on the JADE it will do the operation, that is the content of the data register will be stored in the program counter, and it is a C10 operation. Basically C10 is not any different, but here the way of implementation is different. Now here it's a different complement operations, it is different, so that's why it is a C11. So if we consider these 7 micro instructions on that moment, we can define the control signals in this fashion. Okay, if we define the control signal in this fashion, then we can write the instructions control signals in this fashion. Okay, what is the control flow? First it will activate the C0, then C1, then C2 and C1, sorry, C2 and C3. Okay, C2 and C3, see that these are the two independent operation. Okay, so when it will transfer the output to the instruction register, processor can do the increment of program counters. So for that reason we can consider these two operation at the same time. Processor PS controller can send the control signals simultaneously C2 and C3 at the same time. They can do parallelly, they can execute. Okay, now for the load instruction, what are the operations we have written in this fashion, and here is what are the steps for C4, C6 and C7, and for the add operation C4, that is a C1, so it's C1, and this is a C8, so C8. So whatever the way you have written last time, that is a C4, here is a C4, this is a C1, this is a C1, and this is a C9, so it is a C9. Now for the jump instruction, it is evaluated like this. Whatever the, it doesn't check any condition, so ultimately it has the C10, so it is a C10. But for the jump JADE, another flag JADE have to be checked, and on that moment it is true, so that was same operation C10. If it is not true, it is a false, then it will go to the for next instruction. Okay, now for complement, it will do the complement operation and then again start to the for the next instruction. Okay, so these are the control flow. I hope you can understand this. It is very easy. Do you have any question better here? See that here it is your choice how, what is the structure of processor you want, and based on that you can set up different type of the operations and separate type of the instructions, and depends on that instruction you can generate different types of the operations. It is a little bit depends on you who design the control unit. Clear or not? Prajuta, anyone please ask any question?
No, ma'am, not any questions particularly, ma'am. I just had one question, ma'am. Ma'am, how does the routing? I didn't get how the routing happens, ma'am. Like, how do
I'm
we?
coming. Routing means that what you want to say, how to generate the control signal.
Yes, ma'am. Yes, ma'am.
Yeah, I'm coming that. I'm coming that. Okay, I just want to say here with this slide that what are the control signals and how you can decide the control signal. First one is that first step is that you have to consider one structure, one processor, the where it you have some elements. Element means that you have some registers and you have some execution unit. Okay, so whatever the processing elements you have in your processor, based on that you can choose your sub operations to execute any instruction. Clear? Next step is that if you find out the operations on that moment, you can understand what type of, what are the what should be your control signals. So here just I have considered the operations, and corresponding we considered some control signals. That means when C0 will be activated, on that moment program counter content will transfer to the address register. When activate the C1 control signals, on that moment processor can read the memory, and from a memory address the opcode will be stored into the data register. And when control signal C2 will be activated, on that moment the content of data register, that means where opcode is stored, that opcode will be stored in will be transferred to the instruction register. That means register transfer operations. So for any operations, process control unit should generate one control signal. So here you just define the control signal for one operations. One to one mapping will be there. And for that, if you find out the flow of the control signals, so you can draw in this fashion. Now how to, now already you have done. Now what you can do, see that you can use one, it is a delay element method. So what you can do, one delay you can place, first generate the control signal C0, and for which you have generated the control signal, so you need to find out that the time to complete that operation. Suppose it is a data transfer operation, so how much time will be required to transfer the data. So first one, suppose if you consider the what you have considered the first, here check that what we have considered, that is a program counter value should go to the address register. It is your C0, so it should take some time to transfer from one place to one register to another register. So that time, if you consider the D, on that moment you can place the one delay element, that is a D. Okay, so this is a hardware that can generate some delay. After execution, so it can generate another control signal, that is C1. Okay, so in this way you can give some delay element. See that here D and D1 we consider the different. Here if you program counter value goes to the address register. So these two are the internal component of your microprocessor. So you know that the memory access time, that means memory read and write operation, will take more time than the this type of operation. So obviously that is D1 is more than the D. So this D1 that involves the memory read operation. So whenever processor will do some read and write operation for memory or some other input output device, it takes huge time, or you can say the more time than the internal operation of the processor. So for that reason, here we can consider the another delay, that is D1. Now it can generate, after that it can generate the C3 of C3. Now when it is enabled, on that moment whatever the content of the instruction register, based on that it can generate the one output signal. Now see that here I have considered the 6 or 7, 1 2 3 4 5 6 7. So for that reason you need the at least 3 input lines will be required. So 2 to the power 3, 8 instructions you can consider. So instruction decoder, the size of the instruction decoder depends on your instruction register. Okay, here. So if it is 000, on that moment it will be active. Load instruction will be activated. If load instruction will be activated, again it will generate the C4, and in between C1 and C4 control signals there should be a delay. So C4 control signal is generated for a particular operation, and that operation will take some time to complete. So for that reason we need one delay. So in this fashion, each and every for each and every operation we can do. So now here you can check that for simple jump instruction, it is unconditional jump instruction. So it goes to the program counter value and again go to the next phase cycle. Okay, and for the jump Z instruction, that is a Z is a flag. zero flag, and based on the zero flag, processor can do the operation. If Z flag is set, Z flag is set means that it is 1. If it is 1 and has the jump Z instruction, on that moment, what it will do, it will do the, that is a program counter will be stored with program counter value will be incremented, or sorry, will be stored into the not the program counter, sorry, data register counter will be stored in the program counter to go to the next instruction. Okay, so depends on your Z, you can, that address can be specified. Okay, if it is not, on that moment it will go to the next instruction. Okay, this is the see that here it is the complement means that when Z is not set, okay, on that moment it will go to the this part, see that, for the next instruction. Okay, and here is the complement. So it is a very simple approach. Just only find out the time to complete the operation of a particular processing unit. Based on that, you can place one delay element. But it has many problem also. But how to design, again, I briefly here written that. See, the normal operation of C1, C2, C3. Okay, now T1, suppose it will take the T1 time, it is a T2 time, it is for it is required the T3 time, for which C1 is generated, but it will require the T1 time, and for which the C2 is generated. There to complete that operation, that takes the suppose a T2 unit time. Okay, so on that moment you can find out the delay for the delay unit. Okay, so T2 minus T1 time should be wait, and T3 minus T2 time should be wait to generate from C2 to C3. Okay, now here many to one, how you can design with the help of the hardware. This is very easy, that is a OR. Okay, and if you have any conditional operations, if then else, on that moment you can do, this is a one for X, another for the X bar. That is, if X, that is true, on that way it will do the CI. If it is not true, if X is not true, that means it comes to here and it will go to the CJ. So in this way you can implement the different type of the decision block. It is not very difficult. Okay, it is design phase is very easy, but it has many difficulties. Many difficulties in that sense. Delay element, number of delay element, you can say that what are the operations are required for a particular instruction. So you can say that that number of delay elements will be required. At the same time, to synchronize all the delay, it is very difficult. Another is that to design the delay element, we need, here is also we can implement with the help of software, with the help of the hardware. If we want to implement with the hardware, it is very difficult to design very accurate not the accurate, I don't want to say, it is a to you can say that to compatible of two delay unit, it is very difficult. I give one example to you, that you have many real time clock, not sorry, real clock, with the help of some you can say crystal, you can say that. So the you do not have the exactly same time from all the clock. It is a very difficult. Some clocks may be fast, some clock may be slow. But when you purchase some crystal from the market, considering the same delay, same frequency, you can say that frequency is the same, but still it has some problem. Because of that, if you accumulate some frequencies, only one frequency if you consider for all the crystals, on that moment lag is very small, but cumulative delay for your sum of frequencies, it gives a great delay. That means some clock it will be fast, some clock it will be slow. For that reason, whatever clock we have in our real life, they never can give the exactly the same time. Because of that, it is very difficult to design or to fabricate or to manufacture one clock exactly exactly with the same frequency. It is not possible. So you can understand that same clock, same circuit we use here also to control all the operations, or to generate the different control signals. So what is happen, whenever we are trying to do, it is very difficult as well as it is very expensive to design a perfect delay unit. So for that reason, again, you can say that for a small system design, small control unit design, it is very helpful because it is very simple. Okay, but it is not useful for your sophisticated control unit design for sophisticated processor. Okay, so another method is coming, that is called the sequence counter method. Okay, so here we do not use that type of the delay, but we can use some combinational circuit. With the help of that combinational circuit, we can design the control unit. Now, whatever the micro instructions you have seen for the hardware design, here I have considered the same instructions and same control signals, but way of controlling, way of generating that control signals are the different. Now, whatever the control signals are required to design the control unit for 7 instructions, what I have considered, so that we can control, or we can design in such a way that very easily handle these operations. And that all these operations we can do with the help of some phases. Here we consider the phase. Each phase can generate one or more than one control signal. Okay, now first operation, that is, see that address address will be stored in the program counter. That is the first operation, and for that you have considered the C0 control unit. So you can consider the phase 1. Okay, in that way, fetch instruction from memory, so that is the phase 2. Is increment program counter and decode instruction, that we can consider the phase 3. So whatever the number of operations, we just consider one phase for one or more operations. Okay, now transfer operand address to the address register. This is the phase 4. Okay, now again, that we fetch operands from memory. That means fetch operands from memory operation, that is a phase 5. Okay, now execute operation specified, that may be the addition, subtraction, whatever it is, ultimate execution, that you can consider the phase 6. So in this way, you can consider the different phases. That depends on you. We can consider the phase 7 with the help of the number of 7 phases, or it may be you can do the number of 8 phases. So that depends on you, how many phases you want to consider for all the operations. Now, here I want to explain that how to generate all the signals. You have considered the 6. So for phase 1 to phase 6, if we consider, so how you can implement it? Implementation is very easy. Better here on modulo 6 counter we can use. We know that modulo 6 counter, that means it will start from 00 to 111. So you can have the 8, isn't it? So 3 inputs, the 3 bit output will be there. So 0 to 8, 0 to 7 we can have, and out of that we can use the 6 outputs, and remaining 2 we don't want to use. But here it can generate the pattern 00 to 111, and with the help of the decoder we can find out, or we can get the different we can say that output. So at a time, you know that decoder circuit, at a time it will give the value 1. It depends on your active low or active high your control signals. But here I have considered all the active high. So normal decoder circuit you can place, and see that this will start, depends on your start, that is controlled by the SR flip flop. So when it is 1 and it has the clock, so on that moment you could this sequence counter will start, and if it wants to stop on that moment, through the R you can give the stop signal to stop this counter. Okay, and if you want to reset after completion of one instruction, then it can start with the 0. Okay, so in this way we can design, and depends on your number of phases. If you need the 8 phases, so you have to use this signal also. When it is required, if you consider the more number of instructions. I have considered the 7 instructions, so all these are not complicated, very simple way I have tried to write all the steps. You can write in the different way. Okay, so it depends on you how to write all the micro operations. Based on that, you have to generate all the control signals. Here what is happened, where is that operations better, where is that operations? Okay, this for arbitrarily. Okay, I have used this type of the operations. You can use the different way to implement all the instructions operations. Okay, what are the operations you consider for a instruction? That depends totally, depends on you. Okay, and what is the your assumed architecture of your processor. Okay, based on that you can find out the instruction, and from the instruction you can generate different type of the sub operations. Here I have considered the 7 instruction. It may be, suppose if you consider the 15 instructions, so maybe you need many sub operations. Okay, so for that you may have the different on that moment the number of phase will be more. So suppose if you with the 9 number of phases will be required, so on that moment you have to increase the that is your modulo 6, instead of modulo 6 counter. On that moment you may need the modulo 8 counter or modulo 9 counter. So that count, the size of this counter depends on your the number of instruction, not the number of instruction. Basically that is way of execution of your instructions. Okay, now, what are the instructions, and what are the sub operations you want to use to complete that execution of this instruction. Okay, so based on that you can use the phases, and that phases, the number of phases basically define the size of your sequence counter. Okay, and from that sequence counter, once you have these signals, and you can control all the control signals. Here we have the control signals C0 to CS11 that we can control. Okay, now uh, today I don't want to continue here, I want to stop. So the next class I will be explain that how you can design the this type of the circuit, how you can control all the phases, and all the phases how it can control the generation of the control signals. I will request you, please you take some few you can say that few instructions, where you have studied many instructions. You can find out any number of instructions, and you will do yourself what are the operations, because here difficulties is that to understand these operations, what are the operations are required to complete the one execution. So principle of execution of an instruction in a processor, that you have to know, otherwise you cannot write the sub operations. Okay, here you remember address register, data register, both are the internal register of the processor, and you try to remember data register, sometimes it can be used for your data, and sometimes it can be used for your address. So it can store some address, it can store some data, and at which manner you can use that data, that depends on the instruction. Clear? Sometimes the content of data register, it can be used as an address, sometimes the content of data register can be used as a operand. So that depends on the instruction or way of designing your processing element, and you generate the control signal. Clear? So first you have to consider other type of the instructions. Okay, yeah, instead of the add instruction, you can consider the subtraction operation. Instead of add, you can use the logical or operations, or you can use the or a instruction. That means another different way you can write the logical operations. Immediate operations you can consider. Okay, so consider the different types of the instruction. Based on that, first you find out what are the micro operations will be required. Here I have considered the add. I can maybe I can use the here instruction add immediate, ADI. Instead of the load instruction, maybe I can use the move instruction. Move instruction, you know that different way we can do that. Move means that data transfer operation, that can move from one register. Data can be moved from one register to another register. Sometimes it may be happen, if you want transfer from memory to register. Sometimes it may be happen register to memory. So I will request you, better please you consider some other type of instructions and try to find out the what are the operations. You can ask me next class, ma'am, how we can handle this type of the operations. If you have some problem, you can ask me next class. Okay, and based on that, you try to find out the flow chart. You can say that a control flow, and it is all will be you can I feel that all will be like uh, with the help of what I'll say that, yeah, with the help of this you can implement. You try to I have seen the last semester SR ma'am has taken a very good class how to design whatever the instruction we use in your programming language. Same thing we can implement with the help of hardware. That class is very nice. Class was very nice. SR ma'am has taken. So there she has explained this type of this type of the structure, that if you have different type of the decision block, then how you can implement with the help of the hardware. Okay, so this part, it is very important to find out the to find out this control flow, and ultimately you can place the different type of the data element. Okay, so see that here is used this type of the decision block, and if you can draw all this thing on that moment, just you can place the delay flip flop delay element. Okay, so the placing of the delay element, it is not very tough, but to find out the different type of the logics, for example, here we have the decision, here we have the many to one. So for all type of the instruction, after completion of the instruction, processor will start the execution of your next instruction. So it goes to, obviously it will go to the fetch operation. So many to one, how to implement. So if you can understand all this type of the figure, easily you can design the control unit with the help of the delay element. Okay, so beta, today I want to stop. Monday I
Ma'am,
will
will you,
again
ma'am,
I
will
will
you
take your
upload the
class.
notes to this, ma'am? Ma'am, will you upload the slides to these, ma'am?
What better?
And the slides, ma'am, the slides on the
No,
slides will have.
today's slide I have not given. I have given the last three slides to Abhishek through WhatsApp. I have given, and most probably I have also uploaded in the Microsoft team. You have checked.
Okay. Yes, ma'am. Abhishek sent it to us, and it's also on Microsoft Teams, ma'am.
Okay. And today's class I will upload on Monday. You will have any problem, or today I will be uploaded?
Ma'am, if you could upload it today, ma'am, then we could like check it immediately, ma'am, whether
Okay, I will upload
everything is
today.
covered.
I will upload today.
Thank you.
Okay, but you practice better, otherwise you will have problem. And
Okay,
when
ma'am.
you have the midsem exam?
Ma'am, there was no date given to us yet, ma'am.
No, from this date to this date, the college
Ma'am,
Ma'am,
22 to 27
yes,
March.
22 to 27. Okay. Next day or today, I will convey the message to you, huh, when I will take your midsem.
yes, ma'am.
Okay, so Monday from 1:30, I will take your class.
Okay. Thank you,
Okay,
ma'am.
okay, beta.
Thank you, ma'am.
Okay.
Hello, ma'am.
हाँ बोलो बेटा.
Ma'am, actually, ma'am, do you have, ma'am, a PDF of Rafiqu Jaman, modern computer organization architecture?
Yeah, beta, I don't have. Okay, I will try. because one of my student, PhD student, he is not in station. So I will request him to find out that. Okay,
Yeah,
give
ma'am.
some time. I'll try to find
Yeah,
out the PDF.
yeah. Thank you, ma'am.
Okay, beta.
Thank you, ma'am.
Okay, beta. Prepare for